Hello and welcome to the AICE Chemistry lecture series. Today we are going to look at chapter 10, section 4, which is going to focus on the oxides of the period 3 elements. Now, we already looked at how the oxides of period 3 elements are created in section 10.3, but we're going to now look at the specific properties of those oxides. What are they? What are the oxidation numbers? That kind of thing. And how they change across the period. So what we're going to focus on here is really the trend in oxidation number and other properties of those oxides. Something we kind of looked at with the chlorides in section 10.3, but we're now going to focus specifically on the oxides. This is going to be a very short section, so let's get started. When period 3 elements react with oxygen and create their oxides, or if in the case of something like chlorine, in another way creates an oxide, the oxidation number of the period 3 element is always going to be positive. And this is very simple. The reason why is because oxygen is the second most electronegative element on the periodic table. And as we discussed in the redox chapter, the lower oxidation number, or the negative oxidation number, is always going to be given to the more electronegative element. That means that none of the period 3 elements, when paired up with oxygen, are going to be negative. They're all going to be positive. In fact, the only element that ever has oxygen have a positive oxidation number is going to be fluorine, which is the only element that's more electronegative than oxygen. Since the period 3 elements can use all their valence electrons to bond to oxygen, and in the case of some of them, they can even create expanded octets, the oxidation numbers are going to increase on the oxides as we go from left to right. So if we go from something like sodium to magnesium to aluminum, and if we remember the conversation we had in 10.3, remember that these three first elements are going to be metallic, whereas silicon is giant covalent, and then phosphorus through chlorine. And again, we're not going to talk about argon because argon doesn't react with anything. It's a noble gas. These are simple molecular. Or actually, instead of simple molecular, I should say non-metals. So we'll say simple molecular for their actual oxides. So these are non-metals. So that means that the oxides that are created for the non-metals are going to be covalent in nature, and more specifically simple molecular. No, that is horrible. Then the silicon dioxide that's created is also going to be giant covalent. And the metals are all going to create ionic oxides. So because of this, what we see is that as we go from left to right in the oxides, what they're going to do is they're going to become more complex. Yes, the oxidation number goes up, but we'll get more oxidation numbers with the non-metals because the simple molecular structures allow us to create more than one variable or more than one kind of compound, whereas things like the ionic ones are very straightforward. They only form one compound. So sodium's oxide, which is ionic, is sodium oxide, which is Na2O. The sodium here is a +1 oxidation number. Magnesium creates magnesium oxide, MgO, which has a +2 oxidation number because the ion of magnesium is 2+. And then aluminum oxide is going to be Al2O3, where that aluminum has a +3 oxidation number. So we have the ionic ones, very, very straightforward, very what we would expect. Silicon, which does create a giant covalent structure, but the silicon dioxide, again, has the oxidation number we would expect of +4. as we move from left to right. Again, the numbers just increase. For then when we move to the non-metals, for phosphorus, that tetraphosphorus deca oxide, P4O10, has the phosphorus with a +5 oxidation number. Now this is the only oxide of phosphorus. And it can happen because phosphorus can create some very complex compounds with its ability to form expanded octets. But then when we move to sulfur, we get a different type of variability. Sulfur can actually create two different oxides. And we talked about this briefly in section 10.3. Sulfur, when burning oxygen, creates sulfur dioxide, SO2. But then the sulfur dioxide can then further oxidize with oxygen to create sulfur trioxide, SO3. And then in these two particular cases, the sulfur has a +4 oxidation number in sulfur dioxide and a +6 oxidation number in sulfur trioxide. So you can see here how the pattern is actually kept by that sulfur trioxide. That SO3 has a +6 oxidation number with sulfur, which continues that pattern. But we need to be aware that sulfur dioxide has a +2 oxidation number. Now, there are 3 different oxides of chlorine. Chlorine actually forms 3 different compounds. We're only showing one here because the most common oxide of chlorine and the most stable one is Cl2O7, dichlorine heptoxide. Dichlorine heptoxide is the most stable, most common form of chlorine oxides. And in this particular case, the chlorine, and I'm going to highlight it here, has a +7 oxidation number. That's why it's the most stable. Look at how it fits the pattern, right? +1, +2, +3, +4, +5, +6 in the sulfur trioxide, +7 in the dichlorine heptoxide. This is the most common form of chlorine. Just like with sulfur, though, chlorine actually forms 2 other oxides, which have a +4 and a +6 oxidation number, but those are not as common. Now, if you really want to challenge, take a second and try to figure out what would those oxides of chlorine be. Pause the video, try to figure out what the +4 and +6 oxides of chlorine are. Now, the fact that we have the oxidation numbers should tell you everything, because for +4 chlorine and oxygen, you are pairing up chlorine with oxygen. These are chlorine oxides. So what you have to realize is that if the chlorine is +4, then the oxide has to be, or the oxygens have to equal to -4. Since we know each oxygen is -2, that means we have 2 oxygens to the +4 or -4, and then 1 chlorine. So that's going to be a +4 chlorine. For +6, same logic. If we have chlorine and oxygen, and the chlorine has to be +6, then the oxygen here would have to be -6. Since each oxygen is 2, that means we have O3, so it goes -6 in total, and then Cl, so ClO3. The reason we have 2 chlorines with the Cl2O7 is that we couldn't make a +7 chlorine unless we had 2 of them, because the chlorine will have to be even if there's only 1, because oxygen is always -2. But again, these are not in the curriculum, but they are a good exercise in kind of developing your critical thinking when it comes to the oxidation numbers of these compounds. And, you know, if you see them on the test, you won't be as surprised. You'll be able to figure out what they are simply based on their name and their oxidation number. But that's it. That's mostly what we were going to talk about with the oxides of period 3 elements. Notice the patterns, they increase in electronegativity, and how, as we go from the ionic to giant covalent to simple molecular oxides of the period 3 elements, how the simple molecular ones get more complex as we get more different compounds that can be created because they're covalent, as opposed to the ionic, which always have the same ratio. But that's it for section 10.4. I'll see you all in the next video in section 10.5.